Good morning, welcome back to this course on advanced computer algebra. We are talking about polynomial multiplication in the first part of this course for a couple of lectures. We already started in the first lecture to talk about multiplication, and I gave you an algorithm or a family of algorithms that generalize the idea of Karatsuba multiplication from splitting a polynomial in the middle into two pieces to splitting a polynomial into k equal pieces and then multiply it recursively by applying always the same idea. And we saw that choosing k large enough but fixed, we can get an arbitrarily fast multiplication algorithm, in the sense that it has a multiplication or a computational complexity n to the something where the exponent can be made arbitrarily close to 1, which is the optimum because the input size is n. I cannot expect polynomials to multiply them faster than this. Okay, but then I nevertheless had an improvement, a second algorithm that combined the ideas of this family of algorithms in a way that adapts to the size of the input. And in a rather complicated calculation, we were able to show that this algorithm, this combined algorithm, has a complexity that is better than n to the something for every fixed something that is greater than 1. And so we had reasons to be happy. But then it turned out that this is only fast in theory, in the sense that the n has to be so large that we will never encounter such an n in practice. The problem sizes for which these algorithms that I discussed last time are advantages are so large that these polynomials do not even fit in our typical computer environments, and if we cannot store them in memory, then there's no point in asking what it takes to multiply them. So we are interested in big polynomials, polynomials that are so big that we would never get the idea of multiplying them by hand, for example. Big means things that fit into memory of a real-world computer. This can be quite big. And quite big means things that you nowadays can easily store in a computer. For example, a polynomial that is as big as the file of a photograph. That's not a big thing, 10 megabytes or so. Such polynomials are so big that you will not be able to multiply them in a reasonable time using the standard algorithm, the algorithm based on the formula by which multiplication of polynomials is defined. So we must find an alternative. Karatsuba is already an alternative, gives you some advantage, but we have seen that the other algorithms give you an advantage only beyond the range of problem sizes that we are interested in. So we need a different approach and a more realistic approach, something that is fast not only in theory but also in practice. And this will be the topic of today, and next time we will split the discussion into two parts corresponding here to this, in this table of content, to the sections 2 and 3. So today is section 2. We will assume that we are dealing with polynomials whose coefficients live in an algebraically closed field. Okay, we will then later think about where we actually use this assumption and then how to relax it. But we go one step at a time and assume that the field is cooperative and we don't need to worry about things that are or are not elements of the field. So this is the plan for today. Last time, in the first lecture, I denoted by n a bound on the degree of the factors f and g. Today I want to use n as a bound on the degree of the product of f and g. So that this green polynomial here will be a polynomial of degree less than n, so that it has up to n coefficients, counted from 0th coefficient to the n minus first coefficient. And f and g may be polynomials that have arbitrary degrees as long as the sum of the degrees does not exceed n. So they don't need necessarily to have the same degree. It could be unbalanced, like in this picture, that the f is a little larger than the g. It's just that the sum of the degrees should be less than n. So the sum of the degrees, which is the degree of the degree of h, should be less than n. Okay, and the task is the same as last time. Given the coefficients of f and the coefficients of g, compute the coefficients of h. And I pointed out already last time that when I say given a polynomial or compute a polynomial, then I always mean given the coefficients or compute the coefficients. And this is necessary to emphasize this because the cost of a computation depends not only on the mathematical objects that are given as input or output, like these polynomials f and g and h, but it also depends on how they are given. And there may be different options, and they may have an influence on how difficult the problem is. So, for example, a polynomial, instead of expressing it or representing it as a list of coefficients, I could as well represent it by its list of values at certain evaluation points. You know that a polynomial of degree less than n is uniquely determined if I know its values at n different points. So if I have f and g for some reason given, and I know if I know for some reason the values of f and g at some n distinct points, then those points or those values uniquely determine f and g. And with this representation, I can easily compute the values of h, because the value of h at a certain point is just the product of the value at f at this point and the value of g at this point. And if I have n values of f and g, and I have to compute n values of h, then the multiplication problem is extremely simple. I just have to do n multiplications. It couldn't be easier than that. It's n multiplication, so it means it has a linear amount of computation time that is necessary. A linear number of operations is needed in order to multiply these polynomials if they are given in this alternative representation. Okay. Now, but that's not the problem. The problem that is given is we should work with coefficients, not with values. Or what we can do is, if the multiplication problem is so easy when they are given as values rather than coefficients, and why don't we turn or transform the given data into the other data that represents the same object? So that would be the idea. Here's a picture. So I have f and g given as polynomials, and one thing that I can do, or that I am, in some sense I am asked to do, is to compute their convolution. A convolution refers to the formula by which the polynomial product is defined, and h supposed to stand for the coefficients of the product. So this is what we want, but this is blocked, this road, by high complexity. We don't want to spend a quadratic amount of time. We cannot afford this. So we take a detour and first evaluate both f and g at certain points, so we get the list of values of f and g at some points. Then we do the pointwise product, which is fast, and then we have the values of the product at all the evaluation points, and then we interpolate these values to get the coefficients of h. So here's the same thing written down as an algorithm. F and g are input, h is the product, and at first I choose pairwise distinct elements from the field. Then I compute the values of f and g at each of these evaluation points. Then I multiply corresponding values to get the value of the product. And finally I interpolate these values of the product to get the coefficients of the product. So this looks like a nice idea, but it doesn't solve our problem, because we only managed to make step 3 fast. And okay, this is really fast. This is linear time. We will not spend a lot of time in this step. This will go super fast. But we paid for it, and we paid too much. And steps 2 and 4, we evaluate the polynomials f and g at n points. And in step 4 we compute the interpolation polynomial of n for n given points. And these are operations for which you may remember from computer algebra 1 that they take quadratic time. And if you're willing to spend quadratic time for multiplication, then we can as well use the standard formulation by which multiplication is defined. So this is not a solution to our problem. I have to think a little bit further, and to think a little bit further, we have to exploit that there's something else, that there's some other degree of freedom that we can play with, and it's the choice of these evaluation points. The algorithm, as it's explained here, as it's written there, works for any choice of x, x1 up to xn. Any choice. Of course, pairwise distinct, I cannot use twice the same x. But as long as I choose any n x's from k, this will work. So I can hope to come up with a more efficient algorithm by choosing the x's in such a way that I can do steps 2 and 4 more quickly. And if you have been in my linear algebra class and you know what is coming, because I'm explaining it there, but stay with me, I will go a little bit more into details, and there's a little bit more interesting stuff to say about this that I didn't cover in linear algebra. So the way how we do this is by using the fast Fourier transform, and let me recall or explain what this is. It's based on the concept of roots of unity. So a root of unity is an element of the ground field for which there is a certain power that evaluates to 1. So the exponent of that power is called n. So if n is the exponent of this power, then we say that omega is an nth root of unity. So of course, if you have an nth root of unity, then it is also a 2nth root of unity, because if you square 1, you get 1, and if you square omega to the n, then you get omega to the 2n. So omega to the 2n is also 1. Or stated differently, if something is an nth root of unity, then it's also an mth root of unity whenever m is a multiple of n. So that, but there's some n for every root of unity which is the smallest among all the exponents that map the number to 1. And if n is the smallest exponent for which omega to the n is 1, then we say it's a primitive root of unity. So this is expressed here in different words. We say that an nth root of unity is primitive if its powers are different from 1 when the exponents range from 1 until n minus 1. So that means n is the first exponent for which omega to the n is 1. And using this concept of roots of unity, we define now a certain matrix. It's called the DFT matrix, and it's called the discrete Fourier transform matrix. It's an n by n matrix with entries in a field K, and it's convenient in this context to index the rows and columns of the matrix not from 1 to n, but from 0 to n minus 1, because then I can easily say that in the ith row and the jth column the entry is omega to the I times j, and otherwise I would have to say I minus 1, j minus 1. That makes it more lengthy. So this is a convenient thing. And this matrix is a special case of a matrix we have seen already last time. Last time we had the matrix V, which served as a matrix for executing the evaluation of a polynomial at certain points. So multiplying the matrix to the vector of coefficients gives the vector of values, and this is also what this matrix does. If you imagine multiplying this matrix to a coefficient vector of a certain polynomial, then what comes out is the value vector of this polynomial at the evaluation points 1, omega, omega squared, omega cubed, and so on. So this is what we will use. And so let's see some examples. A root of unity, 1 is always a root of unity, and it's a root of unity for every n, because 1 to the n is always 1. And minus 1 is also an nth root of unity, but only for even n. So minus 1 to the n is 1 or minus 1, depending on whether n is even or odd. In the terminology introduced in the definition, that means that minus 1 is a primitive second root of unity. And to be very precise, I have to exclude the case where the characteristic of k is 2, because in that case 1 and minus 1 are the same, and then it's still a second root of unity, but not a primitive one, because minus 1 to the 1 in that case would already be 1. In the usual number domains that you learn in school, like Q and R, reals and rationals, these are the only roots of unity. The only roots of unity are 1 and minus 1. There are more roots of unity in larger fields. For example, in the field of complex numbers, you get roots of unity for every n. And you find them on the unit circle. So you take a point that has absolute value 1, and you move from 1, which is here, a certain angle that corresponds to 1/n of a full circle. And if we say that this is such a point, then multiplying it means you continue to jump with the same angle around the unit circle, and eventually you end up at 1. So in this case, this omega would be an 11th root of unity. You walk around here, and it's also a primitive 11th root of unity, because 11 is the first exponent for which the power is 1. It's also a 22nd root of unity, but not a primitive 22nd root of unity. Okay, so this is what it looks like in the complex numbers. But there's nothing special about the complex numbers here. As far as roots of unities are concerned, you can consider them only also in a finite field. For example, if you take the finite field with 17 elements, then a 2 is a primitive 8th root of unity, and I don't have a picture to offer you for this. but we can just calculate it. Start with 2 and keep multiplying, times 2 times 2 times 2. Now 16 is the same as minus 1, so minus 1 times 2 is minus 2, minus 4, minus 8, minus 16. Now minus 16 is the same as plus 1. Okay, so 2 to the 8 is 1, modulo 17, and we see here that 8 is the first exponent for which we get 1. So that means it's not just an 8th root of unity, it's actually a primitive 8th root of unity. It's easy to see that in a finite field every element except for 0 is a root of unity, because if you imagine here some other prime instead of 17, and let's say we start with 2 or with 5 or with some value of your choice, and you play this game, you start with your favorite number, and then you keep taking powers. Raise your number to the first, second, third, and so on power, then you cannot always get something new if you are in a finite field, because there are only finitely many elements. So if you eventually, if you go far enough, you will have to see something that you have already seen. But that means you go in circle. You have to go back to where you started, because you can also go backwards. So there can't be a fork. It can't be that you start from something and then you take power, and then here you get something that you have seen before. That's impossible, because if you go from here and you divide by your number, then where would you go? Would you go here or would you go here? The division is unique, so that means that it can't look like this. It must really be a circle where you get back to where you started. And if you started with omega and then compute omega square and so on, then what is the number that you have to multiply by omega to get omega? And the only choice is 1. So this means if you start with omega and take powers, then eventually you will hit 1. This shows that every element of a finite field, except for 0, is a root of unity. It's an nth root of unity for a certain n. Now, the argument doesn't tell you what the n is, but at least you see that the finite fields are full of roots of unity. So there's no danger that we won't find any if we need one. So here's a couple of facts about roots of unity that we will need in order to develop a fast algorithm for executing the DFT. Recall that this is all we need, because we said we can solve the multiplication problem for polynomials quickly as soon as we can do the evaluation and the interpolation quickly, and that's exactly what the DFT does for us. It does the evaluation where the roots of unities are the evaluation points, and the inverse is the interpolation. So if we are done with this, then we are done with the problem. Okay, so let's see what happens if omega is an nth root of unity. Now, one thing you can say is that omega to the k is also a root of unity, and it is a primitive n over kth root of unity. That's one thing. And the other thing is that if omega is a primitive nth root of unity, then the powers of omega, including the 0th power, which is 1, are exactly the roots, the pairwise distinct roots of the polynomial x to the n minus 1. So recall we are in an algebraically closed field, so x to the n is supposed to be is a polynomial of degree n, so it's supposed to have n roots, possibly with multiplicities, but in this case it's really distinct roots, and here they are. So the powers of the roots, the powers of the root of unity are the roots of this polynomial. And the third fact is that if you take the powers of some root of unity and sum them all up, then you get 0. This part is needed in order to prove the next part, which says that the inverse of the DFT is essentially itself again a DFT. So the DFT matrix here, inverse of it is a DFT, but not with omega as a root of unity, but instead with 1 over omega as a root of unity. Surely it's easy to see that if omega is a primitive nth root of unity, then so is 1 over omega. And so that's really a honest DFT matrix here. And the other modification you have to do is to divide by n, but that's also harmless because dividing a vector by n takes linear time, so it's nothing that we have to worry about. So let's see why these things here are true. So remember the proof. The first thing said that if k divides n, then omega to the k is a primitive n over kth root of unity. Let me generalize this a little bit because it's almost free of charge, and say regardless of whether k is a divisor of n or not, omega to the k is always a primitive root of unity, but for the order n over g root of unity. Primitive n over g's root of unity, where what is g? Where g is supposed to be the GCD, the integer GCD of k and n. Okay, so in order to see this, it suffices to first see that it is an n over g's root of unity, so omega to the k to the n over g is, what is this? This is omega to the k n over g, and now you move the g to the k, because the g divides both k and n, so you can write this as omega to the n to the k over g, and this is an integer, and this is also an integer, so I'm not cheating here with things that have no meaning, but this one is 1, so this is 1 to the k over g, and this is 1. So this means omega to the k is an n over g's root of unity. And it remains to show that it's a primitive n over g's root of unity. To see this, let's see what happens if we take omega to the k to the I. Now, if we take some I such that omega to the k to the I is 1. So if I is such that this, we have to show that I must be smaller, or must be a multiple of n over g. That's what we have to show. Indeed, if this is so, then this is the same as ki, and omega is a primitive nth root of unity by assumption. So we must have primitive nth root of unity. From this together it follows that n must be a divisor of ki, because if it's not, it would have a smaller power, namely the remainder of n of k times I divided by n will also be a power, an exponent that throws the omega to 1, and that would be smaller than n, and that would be in contradiction to omega being a primitive nth root of unity. Okay, so this here means that ki is equal to nj for some j, and if you now divide by the GCD, then I can say here, okay, take out the GCD. Then I see that this part here cannot have anything in common with this part because I've divided out the greatest common divisor. So it means that n over g must be a divisor of I. Okay, well that's what I wanted to show. It says that every exponent, which is such that if I raise omega to the k to this exponent and get 1, must be a multiple of n over j. So from this argument here, it follows that omega to the k is primitive. A primitive n over g is root of unity. So from this it follows what we originally stated here in the lemma, because if k divides n, then the GCD of k and n is just k, so that would be exactly this statement. But it also shows a little bit more, because if you go back to this one here, oh yeah, so now this is 11, it means that all the points on this circle, except 1, all the points on this circle are primitive 11th root of unity. Okay, maybe that's a bit too special. Let's see, maybe if I take 1 I minus 1 minus I, then this is a primitive 4th root of unity, but this one as well, because this is I to the 3, and the GCD of 3 and 4 is 1. So by what we have proved here, this is a 4 over 1 root of unity, so it's a 4th root of unity. Whereas this one is GCD 2, 4 is equal to 2 root of unity, also the second root of unity, and so on. Alright, so that was the first part of the theorem, of the lemma. And the second one, well, there's nothing to show, because if you imagine what happens if you plug omega to the k into this, and omega to the k to the n is the same as omega to the n to the k, but omega to the n is 1, 1 to the k is, okay, let me write. So omega to the k to the n minus 1 is omega to the n to the k minus 1. This one is 1, so this one is 0, and this means every omega to the k is a root of extra n minus 1 for every k. But that's part of the story, and the other part of the story is that x to the n minus 1 has at most, like in fact in this case exactly, n roots, and omega to the 0, omega to the 1 up to omega to the n minus 1 are all distinct. And so we are done. These are roots, and there cannot be any further roots, and so that's it. The next one is easy calculation, this summation identity. Okay, so let's see. So what happens if we sum I from 0 to n minus 1, or what did we sum j? Let me see. No, we sum I. But there's also a j here, so I want to know what this is. So we know that the geometric series, now so this is an example for a geometric series, and in general the geometric series says this one is q to the n minus 1 over q minus 1 for all q different from 1. So I can say that this one here will be, well, it will be exactly this. It will be omega to the nj minus 1 divided by omega to the j minus 1. And so omega to the j is not 1 because j is in the range from 1 to n minus 1 and omega is primitive. But this one here is omega to the n to the j. So this is 1 and 1 minus 1 is 0, so this is 0. Okay, and now in order to prove that the inverse of the DFT size n with root of unity omega is the DFT essentially 1 over omega size n. Let's see what happens if we multiply them. So consider the component at position ij. By the way you multiply matrices, you can say this is a sum k from 0 to n minus 1 omega to the ik, because that's the ikth entry of this matrix, times omega to the minus kj, because this is the kjth entry of this matrix. So this is sum k from 0 to n minus 1 omega to the okay, let's put this together. This is I minus j times k, and by what we have just proven, this is almost always 0, and it is more specifically 0 if I is different from j. But if I is equal to j, then I can't play this game here, because here I would have division by 0. But in this case I can say what it is explicitly, because then I have here 0, so omega to the 0 is 1, and I'm summing up n ones. Yeah, so the result is n if I is equal to j. So if I'm on the diagonal, then I have n's, and otherwise I have zeros. Right, this means that this is n times the identity matrix, and that's exactly what was claimed in the lemma. Okay, so now let's see how we can use this. I have already remarked that the DFT is a special evaluation matrix. It turns coefficient vectors into value vectors, where the evaluation points are the roots of unity. And this means that if you have any two polynomials of degree at most n, and you denote by f bar and g bar their coefficient vectors, then you define as h the remainder or the polynomial division of the product by this polynomial x to the n minus 1 and let x to the n let h bar be the coefficient vector of this polynomial, then the DFT tells me how they are related. So we have this matrix vector product is exactly this evaluation. This one is the same for G. Now this is the one that we had also in last time's lecture. This is the component-wise product, because the value of the product is the product of the values. So here you get H so here you get the value vector of H, and then you apply DFT inverse to turn the value vector into the coefficient vector. Now you may wonder why we have here x to the n minus 1. That's because I have now chosen polynomials that can have arbitrarily high degree. So that means previously I said that the degree of f and g should sum up to at most n, or 1 less than n. Now I'm saying independently they just should have any degree up to n. And then we may not be able to recover the full product of f and g because we don't have enough evaluation points. We have only n evaluation points. And with these n evaluation points we can still play this game and interpolate from the values, but then what do we get? If we do the evaluation, if we do the interpolation with an insufficient number of evaluation points, then what we get is the polynomial that we want modulo the product of x minus all the evaluation points. But this here is x is the product of x minus omega to the 0, omega to the 1, and so on. And that's exactly this one. So this is how you probably learned when you discussed polynomial interpolation in computer algebra 1. You can apply it to any data, and the resulting polynomial is unique up to, in this case, this polynomial. Is also what you use in Newton interpolation to go from one step to the next. You would add a multiple of this one to adapt to the next evaluation point that you want to have. But there's a unique polynomial here that has the degree less than n, and this is then this. So we don't get the product f and g completely if the degree of f and g is too high, but we still get something that is related in this way. And if I know for some reason that the product of f and g is less than n, then this remainder of course doesn't do anything, and it will just be f and g, and that would be the application that we have in mind. Okay, but this more general form will be used later. That's why I've already put it here. Okay, so this is the remark. If this sum of degrees is less than n, then this remainder is just f times g, and then we have solved the multiplication problem in the version that was originally stated. Okay, what remains to be done now is to discuss how to evaluate the DFT quickly. So let's look at the DFT. Here it is. The ijth component of the matrix is the ijth power of omega. And what I do now is I prepare this matrix so that I can construct from it a recursive algorithm. I want to do something like split in the middle and reduce the problem to problems of smaller size, a little bit like in Karatsuba's algorithm, where we divided the problem into problems of half the size and got 3 copies of such problems. Here with the DFT, in order to split the problem into problems of half the size, I'll first rearrange the columns of this matrix. here as it stands, the I, or the J runs from 0 to n minus 1 along the columns, and I don't like this. I would prefer to first run through the even J's and then run through the odd J's. And of course I can achieve this by multiplying the matrix from the right by a certain permutation matrix that does this. And I have the even J's here and the odd J's here. And I've re-indexed it in such a way that I let J run from 0 to n minus 1 here, and again let J run from 0 to n minus 1 here. So then 2J minus 1 runs through the odd indices of the original matrices, and here 2J runs through the even indices of the original matrix. I split also along along rows, but here I don't change anything. I just say that I will let I run from 0 to n minus 1 here, and here, so that I can talk about the submatrices, and the submatrices should be again indexed by 0 to n minus 1. So I add, sorry, 0 to n half minus 1. So I add n half. So this one is the entry n half, and then n half plus 1, n half plus 2 of the original matrix, but it's the row 0, 1, 2 of this submatrix. Okay, now let's look at the matrices that appear here in these quarters. This one here. This is easy to simplify, because if you multiply this out, then you get 2 ij, which is the same as here, 2ij from the first factor, and you get n half times 2j, where the 2 cancels, and you get nj. But nj as an exponent of omega is very fortunate, because nj is a multiple of n, and omega to the n is 1. So omega to the nj is also 1. That means this part just disappears. And we have here exactly the same matrix entries as here. This means this block matrix here is the same as this block matrix. Now let's turn to this one. Here I can't quite do the same argument, but I can multiply out and take this plus 1 with the I in front. So I get here a factor omega to the I, and here I get again the same quantity that I've seen already here and there. And for this one I have somehow a combination of the effect that I explained here and the one that I explained here, because here you have to combine the I with this one and with this one, and you have to combine the n half with this one and with this one, and then what happens is, okay, this one and this one is like here, it disappears. This one and this one goes to front, like here, and then there's this one and this one, well, that's this one, and but then there's one more. It's this one with this one. So let's put it here. But so this is omega to the I times omega to the n half. Now what is omega to the n half? We know that omega to the n is 1. And we know that omega to the n half squared is also 1. So omega to the n half should be something which becomes 1 when I square it. But it cannot be 1, because omega is a primitive nth root of unity, so omega to the n half cannot already be 1. But that means there's only one other choice. Omega to the n half must be minus 1. Okay, so here this is minus 1. And now we see here, if we put this a bit more nicely, each of these blocks is a DFT of half the size, of size n half, where omega square is a primitive nth root of unity by the lemma. So it seems here that what I've achieved is, okay, I still have to handle this one. This omega to the I is a little bit disturbing. What does it do? It affects the rows of these matrices. So the ith row gets multiplied by omega to the I, or here by minus omega to the I. But this is like multiplying this block here from the left by a diagonal matrix. And if I do this, can I do this explicitly? Let's say T is this diagonal matrix. Then I see I have 4 copies of the DFT. 4 copies of the DFT, and here this is called T because it's called the twiddle matrix. Okay, that doesn't disturb much because the diagonal matrix is not so problematic, not so expensive. So if I want to apply this matrix to a vector, it's the same as applying this matrix to a permuted form of the vector. And it seems that I've not gained much because I've reduced a DFT of size n to 4 DFTs of half the size. And that's even worse than Karatsuba, because at Karatsuba I've reduced it to 3 problems of half the size. But I'm not done yet. I can take out these DFT blocks because they appear in every block. I can factor this matrix and write it as the product of this matrix and this matrix. Now, okay, now don't be confused by the notation. These 2 matrices have the same format as this big matrix. That's just typesetting. So it's in any case it's an n by n matrix that is divided into 4 blocks of equal size. And also here, so if you multiply this out blockwise, then you get exactly this matrix. And here you see there are only 2 DFTs, and this is better than Karatsuba. Karatsuba has 3, here we have only 2. We have only 2 problems of half the size. This is great. This is very useful. You can simplify it a little bit further and take the t out, so that here you have the identity and the t, and here you have just 4 copies of the identity, one of which has a negative sign. But this is not so important. The important step is from the one that gave us this one, where we have 2 DFT copies. Now, what does this help us? These 2 matrices, or for that matter this matrix, is very simple. It's a matrix that has almost only zeros. It has here a diagonal, and here a diagonal, and here a diagonal, and here a diagonal. I can do a matrix vector multiplication with this matrix in linear time. There's not much to do, it's just zeros. I've just add something with a multiple of something. Each component of the resulting vector, if I multiply this matrix on a vector, is the sum of 2 things that I get from the vector that comes here as input. It's a linear combination, if you want. So this is simple, this is cheap. And what do I do here? Yeah, this requires a little bit more work, because here there's a DFT. But I will apply the same decomposition here recursively, and say, okay, this matrix here has the same decomposition as this one. So I reduce this one to 2 DFTs of size n over 4, and this one as well. And then I recursively proceed until there's nothing left. And how often will I have to do this? How often can I divide n by 2 before there's nothing left? I can do that log n times. So I have succeeded in writing the DFT matrix as a product of log n many matrices, each of which is so simple that I can do the matrix vector multiplication in linear time. And this is the magic in the FFT algorithm, which is just what I just explained, written down as an algorithm. So here it is. Take a vector and assume that the length is a power of 2, so that I can carry on the recursion until there's nothing left. And you're given also a primitive nth root of unity. And the output is the result of applying the DFT matrix to that vector. So it's a recursive algorithm that should have a base case. The base case is when n is equal to 1. In this case, the DFT matrix is a 1 by 1 matrix that contains 1, so there's nothing to do. You just return the f, which in this case is a vector of length 1. Next, you call the algorithm recursively and apply the DFT of half the size with omega square as rule of unity twice. Once to the entries of f with even indices and once to the entries of f with odd indices. This gives u and v. And then you are here. You have carried out this one. This was the permutation that separated odd and even indices. This was the recursive call, and now you are here and you have to execute this matrix. But there I said before that this is just a linear combination. And here it's written down. So the vector has two parts. In the first half, you always take some entry, let's say here the first of the first vector, plus a certain power of omega times the corresponding entry of the second vector. Okay, so this is cheap. This is just a linear amount of time in order to do this. In the second half, you do the same with minus. So that corresponds to this minus and this plus. The multiplication with omega powers here corresponds to the t, and on the front with the u's you do nothing. It corresponds to the application of the identity matrix. This is the FFT algorithm. Surely the algorithm takes n log n operations. We have seen this. There's nothing to prove because we have seen this in the matrix factorization. The matrix factorization consisted of log n factors, and each factor was a matrix for which the matrix vector product can be done in linear time. So I do log n many times, something that takes linear time, and that means it's n log n altogether. Of course, you can also write it down as a recursion, and in this case you get this recursion. So here we have 2 and 2. The log of 2 to the base so the log of this 2 to the base of this 2 is 1. 1 matches the exponent here, and by the theorem that tells you how to solve such recurrences, it follows exactly the statement that I made. This is n log n. So n log n is quite good. N log n is really good. And so there's reason to be happy. What we can record now is that if k is algebraically closed, then any two polynomials, f and g, where the sum of the degrees is bounded by n, can be multiplied with no more than n log n operations in k. And this is the best algorithm we have. Unless you make any specific assumptions, in addition, you will not, we don't know how to do it better. Or you can also say that if you relax this condition here on the degrees a little bit, like we discussed on an earlier slide already, and you say that they are just individually bounded, not their sum is bounded, but the degrees individually are bounded by n, then what the algorithm computes is not the product, but the remainder of the product by this polynomial. And it takes again n log n operations in k. Except that I have been cheating a little bit, so there's still something that I have to clean up. If you look again how we did this, the idea was to use evaluation and interpolation. The DFT does an evaluation here and there, and then I get the values of the product, and then I do interpolation. So all this looks good, and it is good. It's completely correct here. But remember what we had for the formula for the inverse of the DFT. The inverse of the DFT, I don't need an additional algorithm because the inverse of the DFT is again a DFT just with a different rule of unity. So I can use this algorithm, just use 1 over omega here. But that's just almost the inverse. There is in addition a division by n. And that doesn't harm us as far as complexity is concerned, because if I have a list of vectors and I have a list of numbers, I have to divide each of them by n, well then that takes linear time, and linear time is bounded by n log n, so this is okay. The problem is, what if n is not invertible in the field? This could be, because K is an arbitrary field. I said it's algebraically closed, but I didn't say it has characteristic 0. So it could be that n is 0 in K, and then I cannot do 1 over n. So this is a thing that we still have to fix. Now, in our assumption, n is a power of 2, which, by the way, is not a restriction, because this n that I'm talking about here is only an upper bound on these degrees. So if the degrees themselves are not powers of 2s, then I just increase the n to the next power of 2, and that's good enough. I'm just padding the vectors with some zeros. This is no problem. But the problem is if 2 is not invertible. So because the power of 2 is of course invertible if and only if 2 is invertible. So it could be that I have an algebraically closed field of characteristics 0, and then I'm in trouble and I cannot do this. We will fix this by generalizing the DFT mechanism a little bit. So let's look again at this formula. Formula which said which told me how to divide a DFT of size 2n into 2 DFTs of size n. Before I had n and n halves here, but now it's more convenient to have it with 2n and n. So let me introduce a notation, the Kronecker product of 2 matrices. So let's say you have a matrix of size n times n, and another matrix of size m times m. And now I want to combine these matrices to a matrix of size n times m times n times m. So many rows and so many columns. And I define it as a block matrix where each block is a copy of B. So that's all m times m blocks. And I multiply each block with the corresponding entry of this matrix. So that each block is an m by n format, and there are n blocks in each direction. So for each block corresponds to a matrix entry of A, and I multiply B with the corresponding matrix entry and call this the Kronecker product of the matrix A with the matrix B. With this notation I can write this here more nicely, because you see that this here is the Kronecker product well, it's the other way around, sorry. So this is the Kronecker product. If I define it like, yes, if I define it like this, then this should be I2 times dn, dftn here, and this should be in times dft2. So the dft2 is 1, 1, 1 minus 1. So this is the Kronecker product and this is a Kronecker product. And here, okay, this is just a diagonal matrix. So it has the T down here and an identity matrix here. So this is what we will now generalize. And in order to generalize this, I'm not going to generalize it as far as can be. Let's just do it for 3 instead of 2. So the idea is to come up with a variant of the FFT algorithm where we divide the vector not into 2 pieces but into 3 pieces, like we did last time, but not with the objective of getting faster, because we already are very fast. Instead, the objective is to avoid the division by 2, and instead we will get a division by 3 then. So let's play the same game as before. We take the DFT matrix of size 3n, and we divide, or we shuffle the columns of the matrix so that I first get the indices that are multiples of 3 in the first third, and then I get the indices that are multiples of 3 plus 1, and then finally those that are multiples of 3 plus 2. So that would be this one. And there's a certain permutation matrix that does this for me. And according to the rows, I'll split again without changing anything. And then I have these block matrices, so 9 blocks instead of 4 as we had before. And now I can do the same reasoning as before, and it will look very similar to before. So let me do it directly and see what comes out. So we have 9 times something that looks like a DFT of a third of the original size. And then we have some entries that correspond to the T. These are the blue entries. Here we are multiplying the rows of the DFT matrix that is yellow by powers of omega, here and there and there. And here we're multiplying them by powers, also of powers of omega, but squared multipliers compared to those ones. And then we have the green ones, which we didn't have before. Well, we did have them before. That was the omega to the n half in the previous analysis. And there we could simplify it to -1. Now we might not be able to simplify it, but let's just have them as they are. If I factor this, or yeah, if I write this now with the block matrices explicitly, and then I have here the 9 DFTs that I already pointed out, then these are the twiddle matrices from before, and these are the squares of the twiddle matrix. Now I can do the same factorization as before, and I get DFT, DFT, DFT. I'm done. I have reduced a problem of computing a DFT of size 3n to the problem of computing 3 DFTs of size n. Okay, and that gives an n log n algorithm for this exactly the same reason as when I divided in halves instead of thirds. We may want to simplify this one a little bit. So we could say take out the t's to the right here, and then see what this here is. If you look closely, you see this is again a matrix that has a structure of a DFT. So you could write it as the DFT 3 times in, and I'm not certain about the order of these factors. Please check with the definition. It's either this or the other way. And here it's the yellow one which yields the recursive call. Okay. So this is the theorem of Collier and Tukey, who invented the fast Fourier transform algorithm. And here it is in its full generality. Here, if you have an n times mth root of unity, and we define T as the diagonal matrix that contains the nth, the first n powers, starting from the zeroth power of omega. So think here of m is playing the role of 2 and 3 in the two special cases that we considered. Now we need a permutation matrix P that sorts that reorders the entries of the input vector according to equivalence classes mod m, if you want to say it like this. So in the first section you get the multiples of m here. Here you get those that are equivalent to 1 mod m, and then equivalent to 2 mod m, and so on. This defines the matrix P, and the statement is that the DFT of size n times m with the root of unity omega can be factored like this. So again, please check the order of the factors. Maybe you have to change the definition of the factor as you wish, but so that it fits together if it doesn't. So here you have the DFT m with respect to the root of unity omega to the n. And here you have the DFT n with respect to the root of unity omega to the m. So here we have recursive calls because the n is just a little bit smaller than the 2 times m or 3 times n. And here this is a DFT matrix that we don't have to worry about, because in the application the m here will be fixed, maybe 2 or 3, so we can explicitly write down what this what the effect of this multiplication here is. Okay, so from this decomposition, this more general decomposition, we can easily translate the FFT algorithm so that it applies not only to vectors whose length is a power of 2, but as well to vectors of lengths that are powers of 3. Okay? And remember why we did this. The reason was that we were afraid of dividing by n. We may be afraid of dividing by n because n is 0. But in any case, regardless of n, you can multiply the n by the other side on the other side, and you will get this as a correct formula that is true in any characteristic. This is because we checked when we proved the lemma that the DFT times the DFT with 1 over omega as root of unity is n times the identity matrix. So if I don't divide out the n, then it just shows up on the other side. So I can always compute n times what I want. Okay? So that means if I do this twice, 1 for this n and 1 for this n, then I can compute a certain multiple of what I want. Once with multiplier 2 to the k, and once with multiplier 3 to the l for certain k and l. And 2 to the n, 2 to the k and 3 to the l are integers. And in the field they may be 0, but if I write them down as they are written here, then I can look at them as integers. And as integers they are coprime. And therefore by the extended Euclidean algorithm I can linearly combine them to 1. So I can find s and t such that this linear combination is 1. So that means if I have computed this one twice, once for n equals 2 to the k and once for n equals 3 to the l, then s times this one plus t times this one gives exactly h. So that's what we want. That's what we want. And this now works in every characteristic. And it doesn't cost us much, because this GCD, this is for free. This is something we have to do only once. Doesn't depend really on n. It's just a little bit of integer arithmetic. Now the multiplication of s with this vector, this costs something. This takes linear time. Oh, but that's okay. And this also takes linear time. That's also fine. So we now are really entitled to stay, and now without cheating, that we can multiply polynomials over a field that is algebraically closed of any degree n in n log n time. That means using no more than n log n operations in K. So there's a little bit of time left for today. I'll show you a little bit more about the FFT, because the FFT is as such interesting, an interesting operation. So let's have let's look at an additional aspect of the DFT. We have seen this theorem of Cooley and Tukey that reduces the DFT of size n to m DFTs of size n over m whenever m is a divisor of n. So here m, for example, could be 2 or 3, and n is the problem size. N is something big, but think of m as something small. And we used these decompositions of the DFT matrix recursively, and in order to do so, we assumed that the problem size to begin with is a power of m. So for example, 2 to the power of 2 or a power of 3. But that's a bit too much of an assumption. Maybe we don't really need so much of a restriction on n, because the nature of the algorithm is recursive, and at every level of the recursion I can make a new choice. Whether I split into 2 parts or into 3 parts is at every level of the recursion completely independent. And therefore we can also have a fast algorithm for vectors whose length is a product of a power of 2 and a power of 3. We would just start with a problem of this size, and then k times split the problem into halves, and afterwards we would be left with a problem of size 3 to the L, and then L times we split it into thirds until we are down to a problem of size 1. And the Hewlett-Tukey decomposition doesn't only work for 2 and 3, it works for any m. So I could say that the theorem gives us a fast algorithm that reduces the problem of computing the DFT of vectors of arbitrary length to the problem of computing DFT of vectors of prime length, because that's what still has to be done here on this side. So here, this is where the DFT m still has to happen. If m is fixed, well then there's no problem, I just write it in the code what has to be done there. But if m is also variable, well then I have to worry about how to do this DFT. Maybe it's just a small one, but I cannot hope that it is always a small one if I want to have an algorithm that efficiently computes the DFT for vectors of arbitrary length. For example, when I'm in a situation where I cannot just extend the vector by padding it with zeros. We can do this because we are interested in multiplication, but there are other applications where you cannot easily do this. So the problem remains, how can I efficiently compute a DFT of vectors of prime length? The theorem of Hewlett-Tukey doesn't help us with this because it requires that the lengths can be factored, m times m. But there's another idea, and this is what I want to show you before we stop for today. So let's see what a DFT looks like. A DFT always has ones in the first column and in the first row. And these ones are of course easy to handle. It's just a linear amount of time to handle them. So whether I compute the vector, the matrix vector product with this whole matrix or just with this small matrix, that's not much of a difference as far as complexity is concerned. So let's focus on this matrix here that contains all the entries of the DFT, but starting with 1. And remember, we started at 0. So I delete the 0th row and the 0th column and obtain this matrix W. And here's a fact. First, if P is a prime, then P minus 1 is not a prime, at least if it's not 3. And second, if P is a prime, then set P is a field. And third, you may know from an elementary algebra class that the multiplicative group of a field is cyclic. What does this mean? That means if you take away from this field with p elements the 0 and consider this structure together with multiplication, then it is a group. This is the multiplicative group of the field. It's just the field without the 0. And to be cyclic means that it's generated by a single element. So that means there is a field element, so that every other field element can be written as a power of this element. Okay, this is what we will use here. So such an element is called a generator. I'll call it G. So let G be a generator. So that means this is the notation for the multiplicative group. So the assumption is that G is so that all the powers of G together, I've written here for all integers, but of course I don't need all integers because that's just a finite group. Anyway, so all these powers, they will repeat if I take all integers, but all these powers together form exactly the elements of the multiplicative group of set P. Then if I map every element of the multiplicative group viewed as an integer between 1 and P to another integer, another element of this group, also viewed as an integer from 1 to P, then this is a permutation. So here there is a permutation that maps K to G to the K, and I can consider the permutation matrix. So there's the matrix of size P minus 1 times P minus 1 because I've removed 0. So set P has P elements. If I take away the 0, there's just P minus 1 elements left. Okay, so now take this W matrix and sandwich it with this permutation matrix. So if you apply the permutation matrix from the left and from the right, and on one side you invert, then that means that has the effect that these exponents of omega, in the exponents, the I and the j will be replaced by g to the I and g to the j, right? Okay, so this matrix here is this one. But now g to the I times g to the j, that's really g to the I plus j, because that's just the law of how to multiply powers. And that means that this matrix has a very particular structure. It looks like this. So this is a matrix that doesn't have a particular structure. Well, it does have a particular structure, but it's not easy to see what it is. It's the matrix W itself for a certain choice of P. P equals 7. So I've deleted the ones that were here and there. So that's a 6 times 6 matrix. So P is 7. I can write this in terms of generators, but I don't see much yet. I can color them, and you see still not much of a structure. But if you now sandwich the P, this with P on both sides, then you see they are aligned in antidiagonals, these elements. So you see them going like this. Oh, this is very structured. This is very structured. It is so structured that matrices that have this form have gotten a particular name. They are called circulants. And you can check easily that the multiplication of a circulant by a vector can be expressed by a polynomial multiplication. So more precisely, here you may want to check this as an exercise if you like. You cannot see this immediately perhaps, but it's not interesting enough to carry out the details. So let's just believe that this matrix here applied to this vector is the coefficient list of the product of the polynomial whose coefficient are the a's that are written here with the polynomial whose coefficient are the b's which are written here, mod x to the p minus 1 minus 1. Okay, but that means we have reduced the problem of computing this matrix vector product with this matrix of a very particular structure to a polynomial multiplication. That doesn't seem like a lot of progress, because originally we wanted to reduce the polynomial multiplication to a DFT, and now we are reducing a DFT to a polynomial multiplication. It looks like we are going in circles, but not quite. There is a little difference that saves us, and that's that here we have p minus 1. So this product here of these two polynomials has to be computed mod x to the p minus 1 minus 1. That means I can do it with 2 DFTs or 3 DFTs of size p minus 1. And before I said if p is a prime, then p minus 1 is not. And we know how to handle not primes, because p minus 1 would at least contain the factor 2, so I can at least once apply decomposition of Curie-Tukey, and then I get down to something approximately half the size, and this is enough to obtain a complexity that is n log n, even though here I'm not really reducing it to the fraction of the size, but only to the size minus 1. If I had to do that p times, it would be very bad, but I have to do it only once, and then I'm certainly not in a prime anymore and can do one step of Curie-Tukey, and this gives me the complexity. Okay. So this is all I have to say about multiplication of polynomials when the ground field is algebraically closed. And next time we'll see how this technology can be generalized to the case of polynomials where the coefficients are arbitrary, live in an arbitrary ring. This will still make use of the FFT, but we have to deal with the problem that the ring may not contain enough roots of unity. It may not actually contain any root of unity, so we'll have to invent a root of unity without that we have to pay too much for it. So this will be the topic for next time. It gives a very interesting algorithm. I hope you join in watching it. Thanks for watching today.